Hello everyone, welcome back to lecture 11. This is part 2 of lecture 11. So, we will continue the discussion on geographic information system for data analysis, right. So, you can see this particular map and tell me whether you feel that this is a good representation of Earth. Forget about these boundaries. So, these boundaries are not correct, right. So, for any country this boundary is not correct, but whether you see that this map is a good representation or this is a good way of representation, right. So, you see this particular map, what do you feel? Whether the previous one was better or this one is better. So, here obviously you will say that this is a better representation of Earth, right, where the boundaries are properly mapped, right, and all these positions, the value or the latitude, longitude can be identified because you have the location values, right. So, this is best way to represent our Earth. So, when we have the latitude, longitude or the location information, that is the best way to represent our Earth. Can we use a reference system to identify the position of a place? Now, how did you come at or how did you arrive at this values, whether 60 should be here or here, right? How do you know? Whether we have a reference system or whether we are following a standard protocol and by which we are generating the location value for any given position of this particular map, right. So, we started with Earth as a sphere, right. So, initially we started looking at the Earth considering it is a sphere. So, we started with spherical Earth model, which represents the shape of the Earth with a sphere of a specified radius. Here you see you have North Pole, South Pole, equator and this is a circle, right. So, this is a sphere. Spherical Earth models are often used for navigation and for global distance approximation. When we started working on the models, Earth models, we started with spherical Earth model and this was very early days. So, that time it was used for navigation and global distance approximation, whether a country is far from the neighboring country, how far it is, how you are going to navigate through a sea. So, using this spherical model, job was done. May be used for coarse scale map, right. Then we started looking Earth as an ellipsoid. So, we have started working on the ellipsoidal Earth model. So, here once you have the ellipsoid, what will happen? You will have the semi major and semi minor axis, right. So, requires for accurate range and bearing calculation over long distances. Radio and GPS navigation receivers use the ellipsoidal Earth model to compute position and waypoint information, right. So, here you have green prime meridian, equator, then North Pole, South Pole and this is how we were representing the Earth. Then ellipsoid is a 3D figure obtained by directional scaling or affine transformation of a sphere. How you are changing a circle to ellipsoid? Basically there will be compression, right. So, you are trying to put some extra forces here and you are changing the shape of the circle to a ellipsoid or spheroid to ellipsoid, right. So, basically we try to see how it is different from a circle, from being a circle how it is changing. So, the best way of these models can represent the shape of the earth over the smoothen average sea surface to within about 100 meters, right. So, here you have ellipsoid and the pole and equators are marked, right, and then you have the semi minor and semi major axis. So, this is the polar radius, this is the equatorial radius. Now, this flattening F is very important, is a measure of a compression of a sphere along a diameter to form an ellipsoid, and the eccentricity is a measure of how much the conic section deviates from being circular. So, we calculate the flattening and the eccentricity, right. So, this is very simple to understand how we started with spheroid, then we considered earth as a ellipsoid because this is more appropriate representation of our earth surface, right. To understand this ellipsoidal earth model, let us see this particular diagram very carefully. So, this green color is basically the ellipsoid, right. So, this is representing, or this is the best representation of our earth surface, where it is also matching with the sea surface, but it is not matching very well with this topography. When we are having a hill, that particular location is not matching. So, actual surface is here, but the ellipsoid is going from here, because our earth is not a smooth surface, right. However, we can represent our earth with ellipsoid, but these surfaces are not matching with each other, right. So, this is the topography, and here this is the difference between the height. So, this is the ellipsoid surface, this is the actual surface, right. So, here A and B are marked, and this is the geocenter, center of the earth. So, the reference ellipsoids are defined by semi major and semi minor axis. Now, let us see a section. This is the whole earth, but now we will see a section. Now, we understood that global ellipsoid is not a good way to represent our earth. So, what we will do? We will go for a local ellipsoid. So, here you can see this is the local ellipsoid, which is representing this particular area in best way, right. Just see carefully. So, here this is the topography, this is the ellipsoidal earth surface, right, and once we have this, it is representing best way, or it is representing this particular elevation, right. So, the local ellipsoids are the best fitted for a specific country or region. So, this particular case, the global ellipsoid, this one was not able to represent this elevation, this topography, but if we have a ellipsoid here, which may represent a specific country or region, right. So, then comes the geoid. So, it is the equipotential surface of Earth's gravitational field, which would coincide with the ocean surface if the Earth were undisturbed and without topography. Geoid model attempts to represent the surface of the entire Earth over both land and ocean as the surface resulted from the gravity alone. So, here if we forget about the topography, the elevation and the depression, we only consider the gravitational forces. So, if we consider that, then the surface will match with the ocean surfaces, right. So, here in geoid we consider gravitational field and we try to put them into the equipotential surface, right. So, here this is the topography, you see here these dotted lines, it is representing the topography. This is your ellipsoid which we discussed in the previous slide. Now, we have the geoid. So, geoid is the equipotential surface of the earth gravitational field. So, here it is not very well matching with the topography, it is not very well matching with the ellipsoid, but we can say that this particular geoid is representing the topography in better manner compared to this ellipsoid, right. So, considering this elevation of the actual topography, let us say that point P is present here, right, and then you have the semi major and semi minor axis, you have poles here and the equator is marked here. Now, you can see this particular point, the P, and this is the ellipsoidal surface. So, you can see the ellipsoidal surface which is marked here, and this is the actual topography, right, and then we can just see a section of it. Here in this case, the point P is marked which is at the actual topography. So, this point we are trying to represent with this actual topography, and here this is the ellipsoid surface. So, there is a difference between this ellipsoid surface and this is the actual surface. So, none of them are very close. So, it is very far, right. So, it will be very clear once we see the section of it. So, here you have the topography and this is the ellipsoid and this is the point P, right, and this is the height difference between the ellipsoid and the topography. So, this is represented with a small h. Now, we are trying to put the geoid here. So, this geoid will be the best representation of the topography. So, here you can see that earlier we had this point here, and the difference between the ellipsoid and the topography we have represented with small h, and the difference between the geoid and the actual topography, that is represented with capital H, right. So, we have different terms here, very carefully you see. Capital H is the orthometric height, right, and small h is the ellipsoidal height from GPS, and capital N, that is the difference between the geoid and the ellipsoid, that is geoid height, right. So, geodetic height is the height of a point on the physical surface of the earth above or below the ellipsoid, measured along a line that passes through the point on the earth and is normal to the surface of the ellipsoid. So, now here you see this h, capital H, which is the orthometric height, right. So, this is very important. So, actually we are going to represent our height with the orthometric height. So, this capital H we will be calculated using this expression small h minus n, right. So, these two will be used and then we will be calculating the orthometric height. I hope this concept is clear. Now, we will continue this with map projection. So, what is the basis of having all these values? How we decide whether it will be latitude, longitude, what value will be there? So, and how we are representing a particular surface on map, that will be decided based on the map projection. So, a map projection is a mathematical formula for representing the curved surface of the earth on a flat map, right. No flat representation of the earth can be completely accurate. So, different projections have been developed, each suited for a particular purpose. Now, you remember the local and the global ellipsoid. So, for a particular small area or for local region, the local ellipsoids are better. But if you are going for a larger scale, then global ellipsoids will be better. So, similarly, map projection is also developed keeping different objectives in mind. that if you are going for a small area, if it is near to the equator, if it is near to the pole, which projection system will be representing these areas in better way. Map projection differs in the way they handle area, shape, distance and direction. No projection can preserve all these properties. So, this area, shape, distance and the direction, these are the key elements and none of them are able to preserve all these parameters. So, depending upon your objective, if you are more worried about the direction, then accordingly you have to select a projection system. So, this is to explain how exactly we are transferring this 3D surfaces on the 2D map. So, just place a plain paper or tracing sheet on a globe, right, and then from here you just try to use a torch, right. So, what will happen, all these line will be projected here on this tracing sheet and then you trace them on this piece of paper. So, this is how we are representing our 3D surfaces, and depending upon what is the position of this paper, it will be representing the area in better manner, right. Systematic transformation of the features of the earth surface on a 2D map, approximated by an ellipsoid or sphere depending upon which one you are using. Transform a set of ellipsoidal geographic coordinates representing position on the reference surfaces of the earth to a set of Cartesian coordinate representing position on the two-dimensional surface of the map, right. So, here basically you are having the approximated surfaces, it can be your ellipsoid, it can be your spheroid, and you are transferring this information on these maps, right. So, that is map projection. Conversion of curvilinear surface coordinates to the planar coordinate system. Projection convert the coordinate system with distortions such as area, shape, direction and the distance. Some projections preserve two properties, some preserves none of the above, but attempt to minimize distortion in all four. So, we will be having a brief introduction about this map projection because time is limited in this particular course for this GIS. So, if you are interested, then you can refer to my videos from remote sensing and GIS course where this map projection is explained in detail, right. So, now we have the datum. Datum is a set of parameter defining a coordinate system and a set of control points whose geometric relationships are known either through measurement or calculation, right. Map projection can be perspective or non-perspective depending upon their method of construction. Perspective projections are 2D representation of the entire globe or part of it perceived on the basis of the following criteria: type of projection plane, position of the plane of projection, position of light source or projection point, and non-perspective projections are developed mathematically and by integrating and modifying other projection. So, we will be seeing the examples of perspective and non-perspective projection system. So, on the basis of type of projection plane, the two-dimensional planes on which the graticules are projected can be of different types, right. Cylindrical, conical, azimuthal or zenithal projection systems. Here we have put the globe inside this particular paper and then after the projecting, so here we consider the light is coming from the geocenter, right, and that will be projected on this paper. Once you open the paper, you will find this kind of map, right. So, this is called cylindrical projection. Once you see this conical projection system, So, here basically a cone is used, and here this equator, you see here this is the place where this paper is touching this globe, right. So, this area will be the best represented area for this conical projection. Once you open, your paper will be like this. Once you have azimuthal or zenithal projection, so here light is falling on this paper from here. So, once you open, you will have this kind of representation. So, whether it is equator or whether it is pole, depending upon that, you will have equatorial case and polar case, right. On the basis of position of projection plane, the position at which the two-dimensional plane of projection touches the surface on which the graticules are projected can produce projections of the following types. So, here you can see one by one, this is cylindrical, this is conical, this is azimuthal, this is cylindrical projection, again the transverse and oblique aspects, right. On the basis of position of light source or projection point, the point of perception of the source of the light or from where the globe is looked at can be of the following types. So, first one is mnemonic projection. So, this is the first one. Here you can see, here the light source is coming from the center and then this is extended here, right, and you will have this kind of representation. This is stereographic. So, here light is coming from the other end from the pole, and this is the equator, and this is how it will be projected. Now, in orthographic projection, the light source which is coming like this, right, and this will be projected here, orthographic. Non-perspective projections, the projection are not developed on the basis of perception of the projection plane from any point or any source of light, right. So, these are constructed mathematically upon modification of the existing projection and considering different factors and conditions, so that the maximum of the projection properties like shape, area, distance, direction can be preserved. So, we also discussed in the previous slides some of the projection systems, let us say preserving one of the parameter, right. As we discussed in the previous few slides, that some of the projections are capable of handling one parameter, they are best representing this one of the parameter. But when we talk about the non-perspective, here we are not using the perception of the projection and we did not consider any point of light source. So, in such cases, this particular projection system is able to manage all these properties, right. Some of the common examples are sinusoidal projection, right, international map projection for the entire globe. So, this will be the best way to represent the earth and you will have better approximation, because all these values like shape, size, direction all are preserved. So, one of the projection of non-perspective is the UTM. It uses a two-dimensional Cartesian coordinate system to give location on the earth surface. It is derived from the cylindrical Mercator's projection and integrated with the international map projection series to develop a coordinate system where almost the entire globe can be represented, conserving the maximum of the properties. In UTM, the globe is divided into 60 zones in each hemisphere, each spanning 6 degrees of latitude, right, and 8 degrees of longitude. Each UTM zone has its own central meridian from which it spans 3 degree west and 3 degree east of that central meridian. Longitude wise, the range starts from 180 degree west and 180 degree east. So, minus 180 to plus 180. Latitude, the range starts from 0 to 720 degree north and south with the same size of the zone, but above 720 to the pole the size of the extent of the grid changes due to height exaggeration. Used most commonly in GIS platform for defining the projection of the data, because whenever you will be using a satellite image or any parameter derived by remote sensing or the conventional technique, all the maps should be in the same reference system, then only you will be able to overlay them together and then only you will be able to run a query to get the answers, right. So, this is the example of UTM grid. Here you can see how these grids are divided. Now, we will talk about the spatial data analysis, right. After we have converted our data to a reference system, we have a latitude, longitude. Now comes how we will analyze these information or these maps or these data sets in the GIS environment. So, we will talk about the spatial data analysis, right. So, what type of relationship exists between geographic feature and how do we express them. So, to understand spatial relationship and patterns, we have spatial analysis to understand our world, mapping where things are, how they relate, what it all means and what action to take, right. So, once you have the information, then you can go for the decision support system. For geographic pattern, finding optimum routes, site selection and advanced predictive modeling, whether landslide is going to occur at a particular location or not, that can be modeled, and similarly many other hazards can be analyzed and the predictive modeling can be developed, right. One of the important aspect of spatial data analysis is understanding where is my office located, where are my delivery trucks. So, how far it is from one place, whether it is north of my home or south of my home, how far it is. Then measuring size, shape and distribution, how long is the river, how tall is the building. Determining how places are related, which rivers are within 10 miles of a pipeline, have other crimes occurred at this particular location, finding the best location and path, the best route to travel, the best corridor to build a pipeline or the best location to site a new store. Detecting and quantifying patterns, where are the clusters of high expenditure on alcohols, where are the hot spots of cancer deaths. Making prediction, how will a forest fire spread based on vegetation and wind speed or the wind direction, how will store size and travel distance attract or distract customer. So, all these can be done in GIS environment, right. And once we talk about the GIS, we have geospatial or the spatial or the geographic data, right. And once we have the spatial or geographic data, we can perform the spatial data analysis and this can be understood very well. So, this is one of the example of spatial functions which is available or which is possible in GIS environment. So, let us say I have a few points here, all these blue color are the points and I wanted to make a buffer, right. So, in GIS environment I will just give a command that I need a buffer of 1 meter around this particular point, then this will be automatically generated. Here this is a road network, right, or maybe you can consider this as a river system and we wanted to know how much area will be affected by this river, right. Or maybe we wanted to know this is a single lane road and we are trying to convert this to 6 lane. how much area we have to acquire for this particular process. So, in such cases what we will do? We will just run the buffer. So, buffer of the polygons or the polylines. This is another example. Here you have a polygon and we wanted to make or extend the boundary of a particular organization, right. So, because of the population or the work culture, we need to make more offices in this region. So, how to acquire uniformly, how to expand this particular campus, right. So, in that case the buffer will help you how much area you have to acquire to increase the size of a particular campus or of building, right. So, this kind of analysis can be done in GIS and it will help you to ease your work at the field level. Some more functions are given here. So, here A disjoint B, right, A contains B, A overlaps B, A inside B, then you have A touches B, A covers B, then A equals B, and then A approximately covers B. So, all these functions can be done in GIS environment once you have two sets of data captured from two different groups and then you are trying to use them together. So, maybe you have to extract the common boundary for both the data set and then only you will be able to perform any analysis, right. So, some of the examples are here. Erase function. So, here used to remove undesired feature classes in input or output data. So, let us say you wanted to remove this particular area from this particular map. So, you use the erase function, right. Then identify overlay, it is to update the existing database with additional information. Here you have two data set 1 and 2 and then you are updating this particular map, right. Intersect overlay used to extract information from the database. So, here this is the intersect feature and this is the database. So, wherever you have the common boundary you will have the output. Then union overlay. So, here it is to update the existing database with additional information. Aerial extent includes both of them. So, here initially we did not consider this, but when you go for union the boundaries will be used here. Then update overlay used to update the generalize the existing feature or database with additional information. Area extent may change. So, here you can see additional information will be added here. Then one of the most important aspect of spatial analysis, that is the interpolation, because many times what happens, we collect the information in the field, let us say water quality, right. All these values are the point values. So, these are specific to a particular location, right, but in between we do not have any value. So, to identify what is the possible value for these location, we can go for the interpolation, right. So, it is a method of approximating a set of values distributed over a space if some values of the set are unknown. Interpolation is a method of approximating a set of values distributed over a space if some values of the set are known. Interpolation can be used to estimate elevation, rainfall, temperature, chemical dispersion or other spatially based phenomena, right. Interpolation can be performed on vector using a tin surface model. That is the best way, because you will be having the better representation of the nearest value, right. So, here this is one example, point A and B is given here. So, point A is 87, point B is 129 and the distance between these two is 45 units. A simplest interpolation using two distance known point and here you can identify the value for the C, right. So, there are 2 points and the distance between A and B is 45 units. Now, find the value at an unknown point C at a distance of 20 units from A, right. So, this is 20 units. So, this is very easy. So, you can calculate the value of C. So, this is 105.67. This is another example where you have 3 values here and you can calculate the value for D. So, the nearest point would be C and A, and here the D can be calculated, right. Spatial interpolation depends on 2 major factors: sample points with known value in space, spatial interpolation scheme or type, right. So, spatial interpolation can be a global interpolation or a local interpolation, right. So, remember, depending upon the size of your study area, you have to decide whether it is global or local. In global interpolation, every known value is used to determine an unknown value. In local interpolation, a set of known values are used to determine an unknown value, right. So, which one will be more appropriate or true representation, or it will be more precise value? That will be your local interpolation. But when the size of your area is quite large and the values are which are varying in the space, then global interpolation can also be used. So, these are some of the spatial functions which are listed here: IDW, kriging, spline, spline with barrier. So, these are very commonly used in GIS environment, right. So, with this I will end this lecture and we will continue this course. Thank you very much.